What up, crew? It's Mr. Athiad, and I am here to teach you stuff. More specifically, math. And even more specifically, we are going to apply our knowledge of quadratics. You've done some playing with Desmos. Desmos is wicked. It's cool. It's wicked cool. But there are going to be points in time where you are asked to show some manual processing. And even though you'll have access to Desmos and you can use it to check your work, you won't necessarily be able to use it to do the work. It'll be a great backup to show that you verified stuff, but processing things manually, you'll definitely be asked for that. So we're going to look at how to do that today. You've looked at quadratics in this standard form, this ax squared plus bx plus c. It can be very useful. There's a lot of information we can get from that standard form. But it's worth noting that quadratic expressions or quadratic functions can also be expressed in this kind of factored form. Perhaps not necessarily all of them all the time. It does require at least one x-intercept for us to get a factored form. But for the ones we're looking at today, totes doable. You won't necessarily have to be able to do the factoring yourselves, but just recognize that the factored form exists and there's information that we can get from it. So one example of a standard form quadratic equation is this. So y equals 3x squared minus 6x minus 45. If one were to perform the factorization of that, go through the process, they would see it's also equal to this particular factored form. Y is equal to 3 times x minus 5 times x plus 3. Both of these forms have this same a value, this leading coefficient, this multiplier way out in front. And that helps us indicate the direction of opening. We know that if it's positive, well then we have something that's opening upward. Whereas if it's negative, then we've got something that's opening downward and it's forming a sad face. There are some characteristics that we can find from factored form that we might not necessarily be able to directly get from standard form. And we'll see that in one of these next two categories. So one of the features that you have to be able to get is a y-intercept. A y-intercept is wherever you're hitting the y-axis, which means you haven't gone left, you haven't gone right, x is 0. So if you want to find the y-intercept, again, just let x equal 0, where that original equation says y equals 3x squared minus 6x minus 45, we will write y equals 3 times 0 squared minus 6 times 0 minus 45. And then we go through and process that. 0 squared is 0, and 3 times 0 squared then is also 0. 6 times 0 is 0. And then there's that minus 45 kicking around at the end. All in all, that gives us a y value of negative 45. Or we can consider that as a point. It's the point where x is 0 and y is negative 45. So worth noting, standard form, it was just the tail end value since we let all the x's equal 0. So not so bad. We get that info from standard form quite nicely. It's not the worst to get it from factored form either. Again, we're just letting x equal 0. So where it says y equals 3 times x minus 5 times x plus 3, we will write 3 times 0 minus 5 times 0 plus 3. And then just figuring out what that is equal to. So y is equal to 3 times negative 5 times 3. and multiplying all that together. 3 times 5 is 15. 15 times 3 is 45, and there's this negative out in front of it. So negative 45. It makes sense that we got the same answer. Again, you were told, or I guess you had to just trust me that these two were actually the same function. But we got the same answer, so that's probably a good sign. And you could also, again, double check it in Desmos if you want to be certain, but here's us showing how we got that answer. And it's, again, still telling us that the y-intercept is the point where x is 0 and y is negative 45. An x-intercept. An x-intercept is wherever we're hitting the x-axis. If we're on the x-axis, then we haven't gone up, we haven't gone down, we're somewhere on here, which means that y has to be 0. We could try getting that from standard form. If we were to do that, we just write down the equation that we had, but replace y with 0. So instead of y equals all that stuff, it's 0 equals all that stuff. The 3x squared minus 6x minus 45. Often when you're trying to solve for x, you kind of want to get stuff without x on one side, and I don't know, we can see where that goes. Process here. I'd be adding 45 to the right and then adding 45 to the left for balance. So then saying that 45 is equal to 3x squared minus 6x, and these terms can't combine. They're not like terms. We're a little stuck. And so there's a little thought that might pop into the old head brain. Miss T left special instructions to write this down. So it says, wait, I can't keep going unless I solve by factoring. And that's a thought that's going on in our head brains, that we can't quite get this from standard form. Oh, sorry, the thought is going in my head. Nailed it. So the factored form gives us this quite nicely. In grade 10 intro pre-cal applied, you would have had to solve some equations by factoring. The fortunate thing this year is you don't have to do the factoring process, which is nice, but recognizing that we have 0 equals 3 times x minus 5, times x plus 3, we are using something called the zero product property. If you have some things getting multiplied together and the result is 0, then one of those things must be equal to 0. So it could be that this factor over here is 0, this x plus 3. It could be that this factor over here is 0, this x minus 5. It could be that this factor over here is 0, this 3. Well, hold on. 3 can't be equal to 0. 3 and 0 are literally different numbers. So we're just going to focus on the parts that have variables in them. So this splits into 2 possible cases. One of those cases is that x minus 5 is equal to 0. And the other possible case is that x plus 3 is equal to 0. And then we can solve each one of those for x. You're right, stick with light blue. So we have to add 5 to the left, add 5 to the right for that equation to tell us that x is 5. And then subtract 3 from the left, subtract 3 from the right for the other equation to tell us that x equals negative 3. There is still an or between that. but it gives us two possibilities. There are two x-intercepts here. The points themselves are the point where x is 5 and y is 0, and the point where x is -3 and y is 0. Those are our x-intercepts. And again, we could double check on Desmos, make sure we actually get those points. But that is us manually processing it. The axis of symmetry will always occur halfway between any x-intercepts. And I guess you could throw that in. It's halfway specifically. That means that if the x-intercepts are 5 and -3, the axis of symmetry is the average of them. And to take the average of two numbers, we just add them together, divide by 2. So your axis of symmetry is where x is the average of those numbers, 5 plus -3 divided by 2. And then we just have to go through and figure out what that is. 5 plus -3 is the same as 5 minus 3. So that top of the fraction is 2, the bottom of the fraction is 2, and 2 divided by 2 is 1. So this is your axis of symmetry. The vertex is that absolute highest or absolute lowest point for a quadratic function, for the parabola. We know that the x of the vertex matches along with the axis of symmetry. So we already have the x of the vertex. It's 1. We just need to find y. So all we're really doing here is solving for y when x is 1. We can do that from the standard form, or we could do it from the factored form. Both work. So in the standard form, y was, just scrolling back to it real quick, 3x squared minus 6x minus 45. I'm going to take that, replace all the x's with 1s. So 3x squared is 3 times 1 squared minus 6x, so minus 6 times 1 minus 45. And then processing that, 3 times 1 squared is 3, 6 times 1 is 6, negative 45 is negative 45. 3 minus 6 minus 45, well, 3 minus 6 is negative 3, and then 45 down from that is negative 48. And we can get that, again, from the factored form as well. So the factored form had 3 times x minus 5 times x plus 3. So writing the same thing, instead of x minus 5, it's 1 minus 5. And instead of x plus 3, it's 1 plus 3. So we've made that substitution, set x is 1 at the vertex. Let's find y. 1 minus 5 is negative 4. 1 plus 3 is positive 4. And then evaluating that, 3 times negative 4 is negative 12. And then 12 times 4 is 48. So this is negative 48. Same thing both times. Sorry about that. The vertex here is the point 1, negative 48. So, couple examples to try out. These first ones, we're going to create a possible quadratic relation that has these features. In this case, we know it has two x-intercepts and that it opens down. So opens down, that means that it has a negative a value. But these two x-intercepts, we can get those as connected to how we got them from our factored form. So in that factored form, reviewing those steps, we ended up with a couple points. They came from these statements of x. They came from there being a 0 on one side and everything else on the other. And then each one of those things on the other side was a factor of the original equation. And we could note that, hey, this had x minus 5. The result was that x was positive 5. This one had x plus 3. The result was that x is negative 3. There's a sign swap there. There's ways to shortcut it. But essentially, we're going to follow these steps in reverse to get to that form. So noting that here, the factored form must have included an x minus 4. It must have been there because that way this would turn into an x minus 4 equals 0 when we're finding the x-intercept, and then x equals 4. So that must be in there. And similarly, there must also be an x plus 1. So that's pretty decent. We could try saying, oh yeah, y is equal to all that stuff. But don't forget, opens down. So we need a negative a value. Throw anything out there in front. Could be negative 100, negative 72, negative 1. But just put something out there. And then of course, don't forget, it relates to y. I dare you to try, I don't know, the next one. See what info you can get. Just one x-intercept is given, and we know the axis of symmetry. Try figuring that out. See what other information you can get. Pause this video, and then resume in like a solid 5 minutes. All right, good pausing. Welcome back. Let's check out this and see what we know. We have an x-intercept at 7, 0, an axis of symmetry at x equals 2, and this thing opens upward. And we could try picturing this if we want. Draw that image either in our head brains or on the paper. There's an x-intercept at 7. The axis of symmetry is at x equals 2. That's to the left of this. That's like over here somewhere. And this thing opens upward. So this must be mirroring across to get the other x-intercept. And again, opens upward means that we're looking at something that looks kind of like this. But what's that other x-intercept? Well, whatever this particular distance is from 7 to the axis of symmetry, that's the same as the distance from the axis of symmetry over to the left side here. So let's figure out what that distance is. To get from 7 to 2, we have to move over 5. And then from 2, we have to move another 5 to the left. And that gets us negative 3. So this is our second x-intercept. Now, has a positive a value because this thing opens upwards. So putting that together, we can note there must be an x minus 7 involved. There must be an x plus 3 involved. A positive a value could be 1,000, could also just be like the 1 that it is right now. And we must relate it to y. Last one says has n behavior Q3 to Q4. Again, you can picture this if you want. Has x-intercepts at a couple places, and Q3 we have to finish down here, and Q4 we have to finish down on the right. So this is the quadratic we're looking at. We can see that has to open down. Which means that there's a negative a value. So, putting it together, there has to be an x plus 5. There has to be, I guess, an x minus 0. We don't need to write x minus 0. You subtract 0, you just get the same thing back. So we'll just write x itself. Needs to open downward. Could again throw like negative 700 there, but just needs to be anything negative. And still relating to y. In this next example, we've got y equals x minus 3 times x minus 5. We're performing this analysis, but again, we're performing this analysis without the use of Desmos. So we kind of have to figure out what's going on in here. To do that, we might want to follow the same kind of order we looked at before. There's some stuff we can find directly from this form. Some we have to do a bit more analysis of. So for starters, this a value out here, it's positive. There's an invisible 1 out there. So positive means we know this thing is opening upward. And because it's opening upward, like in our head brains, it's doing something like that maybe. That's probably not accurate based on the x-intercepts that we'll find, but it's that kind of vibe. And with that kind of vibe, it does have an absolute lowest point. So we know if it opens upward, it has a minimum. We do need to find the axis of symmetry. We do need to use that to get the vertex. Of course, number of turning points is just going to be 1. But let's find the x-intercepts so that we can find some other stuff out here. So for the x-intercepts, we might be able to shortcut it. Again, like in our head brains, we're thinking that 0 is equal to all that stuff, the x minus 3 times the x minus 5. And that gets us the two possibilities. X minus 3 is 0 or x minus 5 is 0. You might have spotted it already at the beginning, but that tells us that x is 3 or x is 5. So those are our x-intercepts, and we can fill those in. So that's 3, 0 and 5, 0. Halfway between those has to be the axis of symmetry. And what number is halfway between 3 and 5? You can manually figure it out. Again, the axis of symmetry will be the average of those two numbers. 3 plus 5 is 8. 8 divided by 2 is 4. So the axis of symmetry, x equals 4. Now that we have x of the vertex, essentially, let's fill that part in. We can get y of the vertex. We're just going to plug in that 4 to the equation we're given. So y is equal to 4 minus 3 times 4 minus 5. That means that y is equal to 1 times -1. Y is equal to -1 overall. So the vertex has a y value of -1. We should also find y-intercept. And that's y when x is 0. So then y would be equal to 0 minus 3 times 0 minus 5. Which is -3 times -5, which is overall 15. Pretty high up there. Let's fill that in. From picturing it, we can get end behavior, or we can start graphing it to see what happens there. Same for range. Domain, we should know that one already, as we've seen it a bunch of times with all these quadratics. They are infinite in both directions. So from -infinity to +infinity, or in set notation, that's x, where x is a real number. But let's start graphing this thing. So we have an axis of symmetry when x is 4. So 1, 2, 3, 4, found it. I'm going to draw that in to help provide myself a little mirroring line. We had x-intercepts we found. One was at 3, 0. One was at 5, 0. We also had a vertex we found, which was when, x was 4, y was -1. So we can plot that in. And we can also plot the y-intercept. So we've got to count these out as 1, 2, 3, 4, 5. I might just put that 5 marker in. Okay, that's definitely not what I'm trying to do. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So there's that y-intercept. And I can get one more point just based on symmetry. So where this y value of 15 is 4 to the left of the axis, 4 to the right, we should get another one. And we can plot that in there. We can start playing connect the dots. You can, again, check things in Desmos to see if you are correct. But I'm going to go in here. Again, I tend to use real sketchy-like lines just to make sure I get a smooth curve out of this. Because if you try to go like that, you're going to get marks off your shape. Or even if you go like, nailed it, connected all the dots, that shape is a little off. So make sure it actually is a smooth curve. Because even though it seems tedious, it's worth getting as many marbles as you can. Just graphing my parabolas. Arrows at the end to say it does go on forever, ever. Whoops. And that's why we use sketchy lines. And it keeps going up, 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 up. Awesome. This thing is giraffed. And that's about it. There is some practice work for you to play with. So I would probably play with that if I were you. It's been a slice. Tell everyone I say hello. But I am saying goodbye. The end.